So in this video, we're going to introduce the process of adding vectors in 3 dimensions. I'll also show you an example problem that will be relevant for your first homework. So before we talk about this, I just want to review, and maybe you'd expect that the technique for adding vectors in 3 dimensions is going to be very similar to the approach that we used in 2 dimensions. And much like 2 dimensions, there are two different approaches that you can take. Vectors do follow kind of a geometrical rule for addition. We talked about two of them, both the parallelogram law along with the triangle rule. And of course, one could draw on some kind of scaled graph paper and keep very good scale and kind of show very good details. And they could add those together and apply the principles of geometry that they learned a long time ago, likely, like the law of sines or the law of cosines. However, that's not a very efficient approach to adding vectors, especially when there are more than two that you're trying to add. Because if you think about it, those kind of triangle or parallelogram-based approaches are all only defined for pairs of vectors. So what if you have three? Well, you do a pair at a time, right? But then what if you have four, and what if you have five, and so on? So clearly the better way to add vectors is to express them in rectangular form and then basically reduce the process of vector addition to the process of scalar addition. And that's what this is showing you below. Namely, if we're able to decompose each vector that we're attempting to add into a rectangular basis of these basis vectors that we introduced previously, I hat and j hat, of course you know what's coming, we're going to define what the new vector k hat is here in a minute, we can simply add their components together. And then the sum of all those components is the new component of the resultant vector. So that's all that this formula is saying here. If I want to add a bunch of vectors, particularly if there are n vectors, I'm going to number them from 1 to n. I'm going to take the x component of each. I'm going to add them together. And of course, these can be sign quantities. They can be positive or negative. And once I add them, that sum will be the new kind of component, the x component of the resultant vector. So I will write that x component as multiplied by I hat, and I'll do that for each component and so on. Of course, the one thing you want to remember is that in 3 dimensions, you will have an additional unit vector along the z-axis. And remember, as we spoke of last time, your book by convention kind of makes the xy plane in the base or floor of most problems with the positive z-axis following a right-hand rule. So let's look at an example problem, and it will kind of emphasize what I was saying earlier, the sense that really what makes these challenging is being able to interpret the geometrical information that you're given in order to do your decomposition, not necessarily the underlying mathematics. Particularly given the prereqs that we have in this class, I'm sure all of you are more than capable of doing the math once you get the problem set up. It's just a matter of getting the problem set up. So remember, unless you're a very, very talented artist and you want to spend a lot of time on this, typically you're going to be drawing just kind of rough sketches in 2 dimensions in order to represent the geometrical information that you're given. So I'm always, when I do these kind of decomposition problems, I don't attempt to, until we get to the free body diagram portion of the course, redraw the drawing that I'm giving with a high level of realism. I just need the drawing to be useful for me. So I'm going to start by basically saying that the first thing I will do, and I got a new pen just so, like yesterday I was making videos for another class and my pen stopped on me halfway through. So I'm going to stay step 1. I'm going to decompose. And of course, this one won't work because it's probably been in our closet for maybe 10 years. You should come visit us sometime at SAC in the engineering department. It's simultaneously a tour of history and an opportunity to meet me if you want. So you can decompose F1 into components. So the question is, for the information that I'm given, what's the best picture that I can draw? So if you kind of look over on the information that you're given for F1, maybe it's not immediately obvious to see, but that vector actually lives in the z-y plane, or more commonly called the y-z plane. So I'm going to draw this as y, and this is z, and this is positive y, and this is positive z, of course. Always be careful with your signs. And this vector kind of goes out into this positive yz quadrant. But the question is, how can I actually come up with the geometry that I need in order to do my decomposition? So the magnitude of this, we're given to be 500 pounds. Well, we're going to follow the traditional approach where we drop a perpendicular to the horizontal axis, which in this case is the y-axis. I will show vector F1 as a sum of two vectors, one that lies along my y-axis. Notice that that's arranged in the positive y-axis, and one that lies along my z-axis that also ranges in the positive z-axis. I will just write this is going to be F1z. I'm not going to show it as a vector because what I'm really referring to there is the sine length. I will write this as F1y. And the question is, typically we need to get this angle in order to be able to do this problem. And we're not given the angle directly. However, we're told that this forced triangle is similar to a geometrical triangle that has a base length of 4, a height of 3, and of course by Pythagorean's theorem would have a hypotenuse of 5. So if these two triangles are similar, then these two angles are the same. Let's call them both theta. And naturally, we know that the sine of theta is going to be the opposite side length 3 divided by the hypotenuse 5. And the cosine of theta is going to be the adjacent side length 4 divided by the hypotenuse 5. So even though I don't know theta, I know an expression for the sine and cosine, which is, of course, all that we'll actually need here, because I can write f1y, and I'm not going to show that kind of ratio and solving it as we have up until now. We'll just note that this is adjacent to the interior angle theta. So I am able to determine that component by taking the magnitude of the vector and multiplying by the cosine of that angle. And I know that the magnitude of the vector is 500 pounds. And I know that the cosine of that angle, I don't know the angle, but I know that its cosine is 4/5. So if I do that math, it'll be 400 pounds. Do I need to make any sign adjustments? Well, no, because if you look, this is aligned along the direction of the positive y-axis. What about F1z? Well, it's going to be the magnitude of F1 times the sine of that angle. So that will just be 500 pounds scaled by. Remember that due to the similarity in those triangles, that is a 3/5 magnitude, so this will be 300 pounds. So 2 questions. First of all, what's the x component? Well, since this force lives purely in the yz plane, the x component is 0. Therefore, we can write this as 0 x component, y component of 400. And we didn't talk about it, but we don't need to make a sign adjustment for the z component either, because that is in the positive z direction as well. So maybe that's the nicest way to express the vector f1 in terms of its components. So for step 2, I'm going to do the decomposition of f2 into rectangular components. And the way that I can do that, if you look at that geometry that you're given, the first triangle that I would start with, and it's always going to be easiest, is to view it as a z component and a projection of that vector into the xy plane. So here's how I'm actually going to go about drawing this. There's the vector, and it's kind of down in that lower kind of octant, and we see that it has a magnitude, that's what I was looking for, of 800 pounds. And I'm going to choose to decompose this into a component that is along the z-axis and a component that lives in the xy plane. So I'll call that f2xy, and I'll call this f2z. And the question is, for the geometry that we're given, what is kind of that angle of declination from the xy plane? Well, hopefully everyone can see that it's 45 degrees. And what that means is that I can get the z component of f2 by, again, just applying Pythagorean's theorem, right? Because remember, that's a right triangle. The magnitude of the vector corresponds to the length of the hypotenuse of this triangle. So it's just going to be 800 relative to the angle that I am given. The z component is opposite for 45 degrees. Fortunately, it doesn't matter. For some reason, the book is kind at the beginning of the course and actually makes uses 45 degrees a lot, so it's hard to mess up. So 45 degrees, of course, is the square root of 2 over 2. That's like 0.707, but we'll do the math a little bit easier. We'll carry it around as just the sine of 45 now. And in terms of the projection of vector f2 into the xy plane, of course, since that is adjacent to the 45 degree angle, that would just be 800 times cosine 45. Do we need to adjust? That's a question. Well, notice that that z component is going in the negative z direction. So we do need to adjust. So I'm going to write and just say, and usually you wouldn't actually show this separately, but just in case anyone is like skipping through what I'm saying, I'll show a manual adjustment of that z sign. And if you notice this vector, so that's f2z. And the way we really worry about the signs of the component in the xy plane is just to make sure that we're consistent with this is positive y and this is positive x. And if you notice, if we were to project that vector up, as is actually shown in the drawing here, into the xy plane, it is in the positive xy kind of quadrant, for lack of a better term. So here is the projection. This is f2xy. Notice that the information we were given, we were told that it's at a 30-degree rotation about the z-axis. That's going to be in the counterclockwise direction of positive x. So this is 30 degrees. So I can again draw my perpendicular. This is my f2x. And this is my I should be careful there. I have this written as x. It is y, of course. This is going to be my f2y. So I can come up with an expression of f2x by just taking this magnitude, which was f2xy, that is that projection. And then if you notice that it's adjacent to the 30-degree angle. So that would just be cosine of 30 degrees. Substituting in what I had beforehand, remember f2xy is 800, cos 45, cos 30. And then in a similar fashion for F2y, notice that that will also be in the positive direction. It's going to just be F2xy times the sine of 30 degrees. So it's just going to be 800 cos 45 cos 30. So since we're going to be using a calculator anyways to add these, I'm just going to say that I can write F2 as these quantities that I have here, and maybe put a little bit of box around them to keep them easy to find. These are the three numbers that I'm going to need. It is F2x, F2y, and F2z. So let's, rather than actually, again, just kind of putting these into a calculator and dealing with the issue of potentially rounding and so on, what I'm going to do is I'm just going to define them all as variables in my calculator. In this case, I'm going to use MATLAB as a calculator. Not that I'm partial to MATLAB, but it's just open. In a lot of calculators, you will find that you can actually enter vectors in terms of their manual components. So for F1, I'm going to define a variable F1. I'm going to assign its x component to be 0, its y component to be 400, its z component to be 300. I'm going to store that in my memory. I'm going to define a vector x, F2. Its x component will be 800 times cos d. Remember, for the MATLAB calculator, you don't change the units. You just use the specific function to tell it that, hey, that input is actually in degrees, not radians. So for the y component, it will be 800 times cos d 45 times sine cos d of 30. So we clearly, I can tell, just made a mistake when I was writing over my actual, it's like one of these things, do as I say, not as I write. Remember, F2xy was 800 cos 45, so we're multiplying by that by the sine of 30. And you might wonder, because that's, the beauty in life is watching your instructor make mistakes, because you see how they're able to catch themselves. I was going to type in the same thing that I did for my x and y component, and I knew that even if the number is the same, like the case of 45 degrees, it shouldn't look the same. That tells you that something's off. And don't forget that your z component is 800 minus 800 times sine b of 45. Usually, as we remember back to that formula I showed you in the previous video, this happens to happen a lot, where the z component will only have one trigonometric function involved, and the x and y will have two. That's just not, it's not like a rule of thumb. It's just based upon the way the angles that you're traditionally given to describe. So if I take F1 plus F2, I can find that this is the actual value. So I will take and write that out here in components. Now the question is, so I'm going to call it FR. It's F1 plus F2. Is this the way that you want to report your answer? Well, like all things in life, it depends. It depends on what you're actually asked to show. So I'm going to write, I'm going to just use 5 sig figs for now, just because I'll show you why in a minute. So that would be 90 and 682.84 and minus 265.69. So, and this is all in units of pounds, I believe. So what was I saying about what you report? Well, sometimes in my lab, whenever we get it set up, whenever someone can magically figure out how to re-enter an ISBN number to the correct number, you will see that it often will ask you for individual components, but it often will ask you in terms of a magnitude or sometimes some angle measurements. So to keep this short, I'll just say, what if they ask you for the magnitude of that vector? Well, remember, you can always find the magnitude by taking the square root of the sum of the squares. So I'm going to call that FRX squared plus FRY squared plus FRZ squared. And in this case, I certainly wouldn't want to re-enter those approximated decimals that I have. I would instead want to let the calculator do the work for me, in this case, MATLAB. So I'm going to just redefine, I'm going to actually store the resultant as a variable. That way I can get to all of its components, and it helps to actually enter the correct variable name. And then I'm going to be able to compute the magnitude by just simply taking the square root of, and in case I'm showing you this because it is good as an engineer to pick up some kind of scripting language, because what you'll find is that although you're taking tests in class, you're often going to be asked to do this in real life, hopefully, in order to get paid for it. So remember that this resultant vector, it has its components stored as the first, second, and third. So this is like your x component, this is your y component, this is your z component. I'm going to square each, add them together, and take the square root. And that will give me a result of 881 rounded to 3 sig figs by convention pounds. So you could also compute the various angle measures that we talked about so far in the class, but we're not going to do that just for purposes of brevity. On the homework, I'm going to ask you to do a problem that looks like what I'm showing here, where you have 3 different forces acting upon an eye bolt in this case. And you're going to try to find, this is a challenge one, to determine the resultant force acting on the eye bolt
if it's defined by this unit vector. So remember that a unit vector always has a magnitude of 1. So what this is really telling you is just the direction of the resultant force. So what you want to do is see if you can find the magnitude of the resultant force. And I'm happy to help you out with that if you need. Sorry, I kind of stumbled over my words on the end there. I had kind of forgotten before we got to that point what that question looked like. Sometimes they give you these questions and you're like given a direction, and you have to find the magnitude of one of the forces. Those are a little bit challenging because they're an inverse problem. In this case, you will see a little bit of a challenge because if you, anyways, I'll let you play with it. That's part of the fun of doing these assignments. So I will talk to you in the next video.